Reactions, Unit 3, ready and willing. All these involve what? They're all addition reactions, right? We learned substitution and elimination. You need to know what those are, but we really focused in on addition reactions, right? That means we're adding something across a pi bond. Those were addition reactions. Add across a pi bond. Next unit, we're going to learn about adding stuff across alkynes. This time we focused on alkenes. So what was the first thing we learned? We learned about the HXs, right? The HXs. That involved HCl, HBr, and HI. The next thing we learned about was essentially H+. Now for both of these, and actually for everything, we had to be wary about something also being involved here. But remember we talked about concentration, there was always that little, we're always going to make up, both of these always have two things, carbocations, right, for sure. And we know carbocations happen, then we got to be thinking about what? Rearrangements, right? And carbocation stability and how that works. The other thing we have to be weary of or leery of with these is solvents. Remember we talked about solvents and concentration, right? Be leery of those solvents. Be leery of those solvents and the carbocation rearrangements. That's the key to that. The other thing we talked about, all the other reactions we talked about don't involve carbocations, so they don't involve rearrangements. So these are the only two things that involve carbocations. Everything else, no. So no rearrangements, no carbocations. All right, the next thing we learned about BH3 as step 1, and then step 2 was either OH minus or this H2O2. Now there's an interesting part about this. This gave us products that we called anti-Markovnikov. Whereas before, I guess if I'd added one more thing here, these were Markovnikov products. Who remembers what the difference between Markovnikov and anti-Markovnikov is? It has to do with the most substituted carbon. So if I had a pi bond, right, let's say I had this pi bond, carbon 1 and carbon 2, the Markovnikov product would have, right, not the H, right, the OH, the solvent, the Cl, the thing that's not a hydrogen would add to which carbon? Carbon 1. Markovnikov has the more important thing, like the actual functional group, add to carbon 1. That means Markovnikov product. Anti-Markovnikov would mean the OH, the I, whatever would add to the less substituted carbon. That's the anti-Markovnikov product. Right? All it has to do with what kind of product you end up with. So Markovnikov and anti-Markovnikov. If the non-hydrogen adds to the more substituted carbon, right? If the OH, the I, the solvent piece, the ether part, ends up on carbon 1, the more substituted, we call that a Markovnikov product. But sometimes we want the OH or something to add to the less substituted carbon, right? We'd call that the anti-Markovnikov product. One of those cases, actually the only case you know, is with BH3, step 1. Step 2 is OH and H2O2. You need to know the mechanism for the first step, where the boron adds to the less substituted carbon. And that addition is a syn addition, and it adds regioselectively to the less substituted C. All right, because it gives you an anti-Markovnikov product. So it's a syn addition, and it adds regioselectively to the less substituted carbon, right? Which would be like carbon 2 as my example up here. Whereas before, all of these added to carbon 1. Now the second step here, you don't need to know the mechanism for. All you need to do is replace whatever the boron was with an OH. The syn stays the same, everything stays the same. All you do is replace the boron part with an OH. right? Another one we're going to talk about, right, which I just talked about before this, was hydrogenation, which was that H2 and a metal catalyst like palladium or platinum. That was not regioselective, but it was a syn addition, and you're not required to know the mechanism for that. Another thing we learned was ozonolysis. Right, what that did, that involved O3. That essentially, I'm writing cut in quotations, cut an alkene into two carbonyls. Right? You cut an alkene, turn it into two carbonyls. Usually aldehydes or ketones, one of those two. Okay? So you don't need to know the mechanism for that. So no mechanism for step 2 here. No mechanism for hydrogenation. You need to know it's a syn addition. No mechanism for ozonolysis, but you need to know that what it does, it cuts two carbonyls. Right? You know that. All right, so our last one, so I would say this ozonolysis, right, this ozonolysis is not an addition reaction, right? It's almost like a division reaction. It's cutting the alkene in half into two carbonyls. So we have one last addition reaction, and you're responsible for knowing the mechanism, and it's called the halogenation. Halogenation. And that's the one that involves that 3-membered ring, and involves Br2, the bromonium ion, or Cl2, right? The bromonium ion or chloronium ion, right? And these, right, do a trans addition, right? They end up trans. Things add trans or anti. So that's the stereoselectivity, the stereospecificity for this reaction. Is it regioselective? Absolutely. You always go for the more substituted carbon, right? So it's regioselective. Is there a carbocation with halogenation reactions? No. Absolutely not. Because carbocations, of course, are only up here with HX and H+. So how is it regioselective? Let me draw a picture quick. If I showed you a bromonium ion, and I said carbon 1 and carbon 2, which carbon of the bromonium ion do you think is more likely to get attacked by a nucleophile? Carbon 1, because it's more substituted, right? So the regioselectivity here is all about, right? Regioselectivity is about more substituted, right? More substituted. There's no carbocation, but the more substituted carbon, carbon 1, is the one that's going to be attacked by the nucleophile. And you can imagine it comes here on the back side, because that's where sigma star is at, and you get an anti-addition. I should draw there'd be a hydrogen here as well. You get an anti-addition. Final piece to worry about. What do you think the final piece is to worry about for this one? It's very similar to before. You got to worry about your solvents. If there's solvents around, that's what's going to act as a nucleophile and attack things like carbon 1. Also, one last bit, is the bromonium ion going to form just on the top of an alkene, or would it also form on the bottom of an alkene? It also form on the bottom, right? So you got to be careful with that idea about maybe enantiomers forming. So the bromonium ion is going to come from the top and the bottom, and wherever nucleophile attacks, of course, is going to attack from the opposite side, and you're going to get trans products. So this trans anti is talking about the final product, but initially the bromonium ion, because a pi bond is flat, right? Where my p orbitals, right? The top part of the pi bond has electrons, just like the bottom part does. So you'd make this bromonium ion, and you'd also make
Sorry, you mean
this bromonium ion.
You mean anti-Markovnikovs?
This has nothing to do with nothing to do with Markovnikov or anti-Markovnikov. Markovnikov has to do with when you add one thing, right? One thing. So when you make a bromonium ion, you'd make this bromonium ion, and you'd make, right, this other bromonium ion, right? It's an enantiomer. But again, what doesn't change, does the regioselectivity change here? Which carbon is still the one that's going to get attacked by a nucleophile? It's still going to be carbon 1. All right, so finally, right, so hopefully it's clear. Bromonium ions, you're going to make both a top and a bottom version, right, when you add to an alkene, right? You're going to be regioselective. The nucleophile, whatever that is, if it's a Br minus or the solvent or Cl minus, is going to attack carbon 1 in this case because that's the most substituted carbon. That's the regioselectivity. The final products then are going to be anti because whatever attacks here, the nucleophile will be here. This bond will break, and the bromine will be on opposite sides, right? So that'd be an anti-product. So 3 things. Regio, you'd have both the bromine's going to add, so some sort of stereoselectivity, the bromine's adding to the bottom and to the top of a pi bond. When you want to break that bromonium ion, it's going to react at carbon 1 in this case, the more substituted carbon. The nucleophile is going to go there. And when it goes there, it's going to go in such a way that it's anti. It's going to be on the opposite side of where this bromine ends up as this bond, or this bond, in that case, breaks.